Okay, jumping in, good afternoon or good morning, wherever you are in the world today. Thank you for joining the CIROH Research to Operations to Research or R2O2R webinar. This event will feature sessions that will be hosted by our speakers from the University of Illinois at Urbana-Champaign, Dr. Ximing Cai, Anav Vora, and Zihan Zheng. I will let them do a quick mic check and make sure that their screen sharing is all set up, and then we can launch right in.
Yeah, I think we are ready. We're ready to present. Yeah.
Okay, perfect. Thank you, guys.
Should I start, Charity?
Yes, please do.
Okay, good. All right, good afternoon, everyone. I'm Ximing Cai from the University of Illinois. Thanks for providing this opportunity to present our work. So I'm basically trying to present a product developed from my CIROH projects. And the purpose here is to talk about a generalizable open source data-driven reservoir operation code. And hopefully this code can be incorporated into large-scale hydrological models in the NextGen framework. I'm sorry for the long title. Okay. So I also have my co-presenter, my students, Anav Vora and Zihan Zheng. They joined me, and they will also do part of the presentation. So let me go to the outline in the script, please. Oh, good. Here we go. Yeah. All right. So so I will first talk about what are the GDROM. This is our product, and then I will also argue why GDROM, and then particularly to couple GDROM with hydrological models. I will show we're ready to do that. That's basically on the accessibility. And also based on the most recent work and also the new CIROH projects, I'll talk about some existing potential extensions of the product. All right, let me start with what are the GDROMs. So basically, GDROM is a generic data-driven reservoir operation model. So models, they are derived by long-term daily time series of inflow storage release and a climate indicator PDSI, and also the day of a year to represent the seasonality. So basically, we need long-term data. And the process is enclosed two parts. One part is to develop, is to find out the basic operation modules using the so-called hidden Markov decision tree. And the other one is to find out the application conditions. So under what hydrologic conditions, which model should be applied. So put this together, we form GDROMs. So I'm going to show later GDROMs in this way could capture the operation dynamics, like the shift of the module from a crossing season or crossing extreme events. And particularly, I will also highlight a little bit how GDROM capture operators' behaviors, because this is a difficult part for reservoir operation. So we kind of assume reservoir operators, they follow the pre-designed operation curve. But in the real world, especially when they deal with extreme events, they always have their own, they always bring their own justification and performance. And that part is no practical. We don't have much data explicit data to show that. But we assume they are embedded, right? They are kind of included in the historical time series of inflow, storage, and release. Okay, so let me go through a little bit of specification of GDROM. So this model, data-driven model, we only have 4 inputs: a storage inflow, PDSI, day of the year, and users' inputs will determine the daily reservoir release. And so we have a parent structure. To show the modules and transition conditions. And this is an example. This is a very simple example to show. So basically is is a tree-based, right? It's a tree-based model. And the red part shows a particular module, like module 1, based on some conditions. What does a module look like? Actually, it is a decision tree. It could be explicitly writing in if-then conditions. So that's why we could actually write all modules in text file, and that makes the accessibility much easier. All right, so we apply GDROM to 450 or 250 reservoirs in the contiguous United States, and each of these reservoirs has more than 15-year daily operation record. So one interesting we found is that the operation of any of the 450 reservoirs could be represented by 1 to 8 modules. So from the map on the screen, we show all these 450 reservoirs. The shapes represent the reservoirs with different primary operation functions, and the colors shows how many modules for each of the reservoirs. So as we can say, many reservoirs, by this below color, many reservoirs, they just have one module. So we know that for some like irrigation, some dams or reservoirs used for irrigation or for recreation, and their operation is basically simple. They keep kind of constant flow. And so most of the reservoirs, especially with flooding control irrigation, water supply, and they could be represented by 2 to 5 modules. Right? It's a little more complex. But on the other hand, we found only a very few reservoirs among these 450. The modules, the number of modules is more than 6. So that's kind of a good thing. That means actually reservoir operation models may not be that complex, right? The basic modules is the number of the basic modules is limited. And further on, we find out all these modules, they fall into 5 basic types. So as I showed by this diagram, we have a constant release, just simple constant release. We have piecewise constant release with inflow, and piecewise constant release with storage. And the linear relationship, release increases linearly with inflow. That's understandable, especially in high flow season. And the last one shows is kind of nonlinear relationship, how the release changes with the storage. And this is exactly the well-known hedging policy. So it means to some extent, we have to keep storage for future. And this is widely used in drought period if a drought is forecasted. And so I mean, among hundreds of modules for all these 450 reservoirs, they all belong to one of these 5 modules. And some reservoirs we might say are combined, right, with kind of combined types. But this reminds us actually, we could use these 5 basic modules as Lego bricks and to build different shapes as we want. So for certain purpose. So explicitly, we use these 5 Lego pieces to build reservoir models with different module combinations, right? Different combinations. So for a given reservoir, we apply a series of these modules across seasons, across years, with possible changes of the model applications. I'm going to show some details over there. So, all right. So now basically the following few slides, I'm going to show how GDROM captures operation dynamics. So this is for aqua reservoir in Utah. It's a reservoir used for multiple purposes, including recreation and water supply for water supply or probably also irrigation. And we found this reservoir could be modeled by only 3 modules, right? Only 3 modules. And as we can, the modules are marked by different colors. So this is blue, pink, and red. So from the storage curve and also the release curve, we can see that basically we have this kind of intra-year cycle. right? Inter-year high flow, low flow cycle, or low storage, high storage cycle. And over years, we have pretty much consistent, right? For most of the reservoirs, over years, we don't have dramatic change. We have quite stable operation roles. And that's observed for most of the reservoirs in the real world. Okay, let's look at the Bighorn Lake. I think this reservoir is in Wyoming. And I want to use this reservoir to show how GDROM responses to drought events. So around 2000, starting from maybe 2001 to about 2005, you can see that the PDSI, the inflow is quite low, the PDSI is quite low. That represents some continuous drought period. And you can see that one particular module 2, right, in red, that one has been used consistently, right, in this drought state. And that basically shows the reservoir operators, how the reservoir operators they respond to this drought issue by a particular module. And also if you look at the Taylor Park reservoir in Upper Colorado, for this one, I particularly want to show the module, the kind of long-term module application changes. The frequency change, we believe that some will reflect the operator's behavior change. So for this reservoir, we have 4 modules, start from M0 to M3. And M0 and M3, they are constant. They are kind of constant modules applied in no flow time period. As we can see that from 1999 to, so this basically from 1999 to 2000, right? So module 0 as a constant module is more frequently used. But then starting from early 21st century, for about 10 years, that module was switched to module 3. This is also constant flow, but this represents, and this constant flow with relatively lower value, lower reduce, right? So during the season, into the year, we can, this is another thing we can say, into the year, in the high flow time, we can see that. So basically, people alternatively use module 2 and 3 to deal with the seasonality. So this one basically shows the reservoir operators. They usually we don't have the so-called stationary operation roles. They change over time based on the change of the environment, especially the climate and the wind level. All right. Anyway, so far I talked about YG, basically what are the GDROMs, and I particularly show some features of GDROM and also and how GDROM reveals the dynamics, operation dynamics, and also the operational roles over time, and also into year. Now I'm going to switch to why GDROMs. Okay, why we think this one might be a reasonable reservoir code for large scale hydrological models in NextGen. Okay, so we use 4 criteria to assess generalizable open source reservoir code in NextGen. The first one is the interpretability. So we all know, so if we use machine learning models, we often end it with the so-called black boxes, right? It's not, it's difficult to interpret the results, but we use apparent structure, and the interesting thing is that we only have 1 to 8 basic modules, and we can explain which module is for what purpose. That's one thing. And the other one is that we, based on the figures, the slides I just showed, so GDROM GDROMs reveal the operation dynamics over years and within a year, and also some operators behavior representation. So this is interoperability. The other one is generalizability, generalizability. So we have 4 common inputs. And the important thing is that all these inputs, they are independent with reservoir characteristics. We don't need the reservoir size, right? We don't need the reservoir size. And we believe the reservoir size is somewhere embedded in the data. So that makes it, this is a general feature, right? And the other one is that this generalizability is reflected by the 5 typical common types of models, right? So we use them as Lego pieces to build any model, this generalizability. Now, we move to the compatibility. Why is this important? So for many of you, if you are familiar with the reservoir operation, you might know in the literature, you can find thousands of studies, and they show how complete, how good, or how comprehensive their reservoir operation models using multi-objective optimization, this and that. So I see Fred raised your hand. Fred,
I did. Ximing, your audio sounds very muddy. If you could get closer to the speakerphone, I think we could hear you better. Thank you.
All right. Okay. Thank you. Let me. I have to change. Let me change this. Okay. All right. Thank you.
That's much better.
Oh, okay. Here we go. Is that okay? Is that better?
Yes,
Hello?
that's a lot better. Thank you.
Oh, okay. All right. Let me sit down and speak closer to the microphone. All right. So we have a lot of models, right? So many of them, they are built with optimization, and they have multi objectives. They are you can say they are very comprehensive, but they are also very complex. The solution might take more than 1 hour or even longer, right? And we also have some very complex simulation models. So how could we couple those models with hydrological processes? So that might challenge our computational issue, right? So that's why we think a simple structure would be really important. And the other compatibility is that we have explicit input-output relationships with rainfall runoff processing, and allow my students, they're going to show how could we couple GDROM with rainfall runoff processes. You're going to see details over there. And the third thing I want to say is that we are ready. Some of our products, we are ready to test and use for any watershed rainfall runoff models or basin rainfall runoff models. So this is about compatibility. Now, let me move to the last one, is reliability. Obviously, this is quite important, right? So our current product with the 452 reservoirs, they are all derived from long-term historical daily operational data. It covers many of these reservoirs are actually, the least number of years is 15, but many of them, they have 30 or even more. I did not put the right number over there. So that means the data covers a lot of things, dynamics, historical, policy changes, and also environmental, like inflow changes, right? So this long-term data series could make the model kind of comprehensive to capture all possible cases. The other thing is that we have validated the results with 452 large reservoirs. So I'm going to talk about some of those. And we have done testing with watershed, basin, and the national scale hydrological models. I'm going to show some details next. Okay. So in general, we assess, we think this generalizable reservoir code can be evaluated from these 4 aspects. Okay. Now let me show you like our results by coupling GDROM with watershed models, basin models, and national models. And I will argue how our model improves the performance. So when we talk about including reservoirs into hydrological model, And we all know many of our models, we just ignore reservoirs. We don't really have a very realistic way to represent the reservoirs. And what does that end? That could end with biased parameter estimate. I mean, you might calibrate your model to observe the flow, but inside of the model, your parameters may not make much sense. The other way is we call this as loosely coupled models. So basically, we just say, all right, so we have a good hydrological model, and that could be used to simulate. That's not affected by reservoir. That could generate reasonable inflow to the reservoir. And then we run our reservoir model, right? But in this way, it is subject to a very serious assumption. So that means we have this natural watersheds or basins to calibrate our hydrological models. But unfortunately, today, around the world, we could find very few natural basins, right, to calibrate our hydrological models. The more realistic way is in the context of coupled elimination systems. So we need to move to this fully coupled model. So in other words, we need to treat reservoir as an internal element of the hydrological model. And then we calibrate the model together, right? We calibrate the model together. So now in our work, actually, we try to promote this, right? We want to incorporate the GDROM as an internal component of a hydrological model. So now I'm going to show some results for this watershed model. So we chose 5 watersheds in different regions of the contiguous United States, as you can see from this. So most of those, all of those, they have one reservoir, just to make it simple. And also we have each of this watershed includes multiple flow gauge stations, right? Then we can check if the rainfall runoff path, the stream flow path. Okay. All right, I'm sorry for this very complex figure. So you might be confused by this complex drawing. But let me explain. First of all, in the literature, especially in the global hydrological model practices, we already have some well-known reservoir models. Like if you work on this, you might notice Hana, right? Hanasaki. This is probably one of the most popular, most earliest one or popular one used in global hydrological models. And we have some recent ones like iStop. That's developed based on some, just like GDROM is developed based on some data products. So we want to, so in the figure, you can see that from on the vertical side, we list all these models, and for each of the model, we show the distribution of the calibrated parameters. So from up to down, we have 12. This watershed model has 12 parameters. If you're interested, I listed all these 12 parameters here, and some of these parameters, so you can say for each of the parameter, we provide not a single value of the parameter. We provide a range, right? A range of the parameter values and with each of the reservoir modules. So let's go back to the 12 parameters. Some of them, they are related to, they are probably much related to reservoir operation. Some of them, they may not be that much, right? So we particularly want to look at these 6 parameters. They are more related to soil moisture. And in the literature, there are already a lot of studies they found if we have an unrealistic reservoir operation, or we ignore reservoirs, watershed model, then the soil moisture part could be very unbalanced. Right now, let's just look closely how GDROM does, how other reservoir operation does. So on the top, we have a so-called inflow, right? So-called inflow, and this one shows this one shows, this one basically, the parameter is calibrated, is estimated from the watershed part without any reservoir interference, right? That's why if I go back to this slide, so I can't do this way. Yes. Oh, right. Yeah, so you can see here, right, above the reservoir, above all this reservoir, there is no reservoir, no other reservoirs, right? So we can treat them as a kind of natural, we can treat them as a watershed without the impact of reservoir storage, right? So the parameter under this inflow scenario is from that part without the reservoir. And we are, because this one is not affected by reservoir, we assume the reservoir, the parameters is not disturbed by reservoir operation. And then you can say the distribution of the parameters from let's look at this, from the 6 models, right? From the 6 models. So we argue from one of these models, if the parameter distribution replicates or similar with the parameters estimated under the case without reservoir operation, then we think that model, the parameter estimation might catch more reality. So as you can see here, compared to other models, GDROM basically, GDROM in terms of the shape of the distribution and also the location of the distribution, GDROM does a better job than other models, number one. And number two, you can also say for some parameters, for example, for this parameter B and parameter KD and ASS, and we don't see much difference. There are 2 reasons for this. One is that those parameters are not really affected by reservoir operation, number one. And number two, it could be like none of these reservoir models catch the truth, right? None of this model catch them. That's still possible. We don't want to hide that. But if we look at the last one, the base flow recession coefficient, we know this one is pretty much, base flow is pretty much affected by reservoir operation. And now for this one, you can say that the actually GDROM generates parameter distribution quite close to the reference case, to the baseline case. Okay, much better than other models in terms both of the shape and also the range. Okay. So in conclusion, so here we want to say if we fully couple a GDROM with a watershed model, we could end with more reasonable parameters in terms of their distribution, their magnitude. Now, next, I want to show some of the regarding the outflow, right? Because once we couple the reservoir with the hydrological processes, we check to what extent the reservoir outflow matches the real world condition, matches the reality. We use 2. First of all, this figure is also complex. I'm sorry, but first of all, we compare over models, right? We compare, one case is that we just ignore reservoirs, and the other, we have these 5 models, right? We have these 5 models. And also we compare the those coupled models I mentioned earlier. So we calibrate a hydrological processes model without considering the reservoir as an internal component, and fully coupled models. This is on the right, right? Loosely coupled model is on the left. A fully coupled model is on the right. And this one, basically, so we want to look at the kind of difference they make. Okay, and then and also we from this figure from KGE, right? From KGE, we can basically say that 2 models, GDROM and the DZTR, they are doing better. They have higher KGE values, right? In terms of the average, in terms of the distribution. That's one thing. And the other thing is that FCN on the right, FCN is doing better, right? It's doing better in the outflow performance. And then on this figure on the right, on this figure on the right, we show the same thing for log NSE, because in general, KGE is more on the high flow and the intermediate flow, and the log NSE is more on the low flow, right? So you can see that for all kinds of flow, no matter it's high or low or intermediate, GDROM is doing a better job than other models. And this is shown for the Folsom watershed, and we have similar results for all other 5 watersheds, and this is too complex. I will not go over the details, but they all confirm our conclusion. GDROM is doing better in the stream flow simulation. Okay, so now we move to a big basin model. So we couple GDROM with the Mississippi River Basin. And from this figure, you can see that there are many reservoirs. Most of the reservoirs are located on the tributary of the Mississippi River. And these reservoirs are used for different purposes, right? And now, we compare KGE, basically the medium and the high flow. We compare the KGE without reservoir representation and with GDROM representation, right? And this dotted red line represents the 45 angle line, right? Basically, they show the identical of these two values. But as you can see that, I want to mention each of these points represent a gauge station, represents a stream flow gauge station. Now you can see that for basically when KGE is in a lower range, and we can say GDROM significantly increases the KGE, as we can say, for example, for this point, the distance of this line shows that. But if you look at the upper part, the KGE is already high. So why we don't see much difference? And this is probably because 2 reasons. One is that in those places, those gauge stations are not much affected by reservoir operations, right? So that's and the other one is basically the other one is that because the KGE is already high, right? There's not much space for improvement, right, for these 2 reasons. So now let's look at a little bit more details. So I have 12 figures, each for 1 month, starting from January to December, right? We use this set of figures to show some change over months from low flow to high flow for the whole basin. And so what we show here is basically the difference between the mean flow, right? Between the mean monthly flow with or without GDROM, with or without GDROM. And that difference is represented by the sine log changes, in order to cover a wide range. All right, so by this definition, you can see that the red color here, you see the red color right here and there. Red color here represents the decreased flow. So which means with reservoir, the stream flow decreased, right? Decreased compared to the case without reservoir. And then the below one shows the increased flow. And you can see this might make some sense, right? You can see that in low flow time, along the main stem, we have increased the flow. So, and then in the high flow time, we have decreased the flow. And that reflects the function of reservoirs, right? For flow regulation. We want to reduce the high flow and increase the low flow. So these figures show some reasonable temporal temporal changes. And the other thing is that we can look at, you can see that we have some spatial heterogeneity. So if you look at some places, they have increased flow, some places they have decreased flow. Why is that? So let's use July as an example, right? So in July, this is a high flow month. So on the main stem, so we have decreased flow with reservoir. But why do we have increased flow on tributaries? So I mean, we could explain in this way. So many of these irrigation reservoirs, major water supply and irrigation reservoirs, they are located on the tributary and not on the main stem. Okay, but in this model, we only use regarding multiple human interference. We only considered reservoir. We did not consider irrigation. Okay, so that means the irrigation consumption is not taking off. If that one is taking off, then we will probably show, we will not see so much increased flow, right? So that also shows for a final accurate model, right? Reservoir is an important thing to consider, but we also want to consider other major interventions like irrigation. We are actually working on that. Okay, so now I move to some testing exercise with national water model. I'm okay with the time. Okay, so for this is not like a tightly coupled model. So basically, we got the NWM simulate the inflow and outflow from a historical period. We use the NWM version 2.1. I know we have a new version, but when we work on this, we could only access this version. All right, and then we use the inflow provided by NWM, and we try to replace the existing reservoir module within NWM by GDROM. Then we could show how GDROM-based model would produce some improvement, right? So that's why here we have NWM plus GDROM, NWM plus GDROM. But here we also show a little more details here. This is a published paper. We will show the impact of the storage, input storage. To simulate release and storage both reasonably is not really easy. So we found out from GDROM sometimes we have some systematic error on storage part. So that's why we try to say, all right, if reservoir storage is available from remote sensing or other purpose, then we could simulate those observations into the model to some way adjust the model. Right? So basically, we show how the observed storage might improve the model performance. And the third thing we look at is how does the inflow, the quality of inflow affects the results, right? If the inflow itself is unreasonable, then we will not be able to expect any reservoir model to generate a better results, right? So how good the inflow simulation is. So actually, we just did some, and this is a figure we made based on the results from National Water Model NWM version 2.1. And here you can say in many places, actually, we have good NSE, right? Good performance, but also in other places, we have relatively low NSE. So that means the some part, especially on the low flow, low flow part, so the NSE may not be that high. All right, so now let's look at the results. Look at the results. So here we compare. So here we have three things. We have existing national water model. We show the KGE. And then we also, we did this assessment on two groups. One is that we include all flows. So like we don't differentiate NSE positive or negative, right? We include all inflow. And the other one is we only consider the more reasonable inflows simulation. And this is represented by the red part. As you can see that the KGE value is significantly higher than the overall cases because the inflow is much more improved. By the way, here we compare the KGE with the reservoir outflow, right? And then the next case is NWM plus GDROM, but we use the observed storage, or we use the GDROM provided model storage, right? So for the KGE, as we can say here, they basically for the coupled model NWM plus GDROM with observed storage are similar to the processes. We have the higher, right? We have the higher KGE in terms of both the average value, the mean value, and the range. All right. Then we also compare this with NSE and the TMS RMSE. So the KGE and the NSE they are more often used to measure the high flow and intermediate flow. MRSE, just like log NSE, they are more appropriate to use to record the low flow. Okay, but now you can also notice that for low flow, right? For low flow, although we have a little bit of improvement, we don't have much improvement actually compared to the original NWM. Why is that? So one of the reasons we're thinking about is that because the low flow is not well simulated in the model. And this is not what I said. This is stated in many publications, right? So that again, that also shows if the inflow simulation is not good, then we cannot expect the reservoir model makes a magic. All right, and then we also say here we show the improvement, the comparison between these three cases for these different indicators for different regions, right? For some regions with high reservoir storage, like Upper Colorado region, and we say the NWM plus GDROM with observed storage could have much higher performance, much better performance. But for regions without large capacity comparing to the runoff, comparing to the stream flow runoff, like the Ohio region, we still see some improvement with GDROM, but it's not obvious. It's not really obvious. So that basically means the presence of the reservoir capacity also affects the performance. And for regions with higher reservoir capacity, we need to pay more attention. All right, so now I finished the second part, why GDROM, and now we want to show why we are, how can we say we're ready to share some of our products. So Anav is going to talk about accessibility of GDROM.
Great. Thank you, Dr. Cai. So I'll be talking about the accessibility part, essentially going over the methods, how we can obtain the GDROM rules, download them, how we can get them, and how we can interface these GDROM modules and models with our existing hydrological models. And these are the same methods used in developing the results that Dr. Cai was recently talking about at the watershed scale or the large basin scale, etc. So I'll be beginning with how we can do the interfacing. And for this particular example over here, I'm going to assume that our distributed hydrological model is a gridded model. Of course, I'll also talk about how we can use it if it was not the case, if we had a watershed type or a vector-based model. But assuming it's a gridded model, what essentially happens inside is GDROM becomes a part of the routing algorithm. So if a grid has a reservoir present in it, then we would use GDROM to route flows through that grid. Otherwise, we'd use the natural routing, which is already existing in the hydrological model. So assuming we have a grid and we are using GDROM to route flows from that grid, there are two parts over here. The first one is the module detection function. As Dr. Cai showed, the tree-based algorithm, which tells us which module to use under which condition. So the module detection function, it takes inputs of the simulated inflow from the upstream in the hydrological model, and the reservoir storage, the PDSI, and the DOI. So if you're running the model with modeled storage, that GDROM provides the release and we update the storage, and we only need the initial storage over here, and then the module detection function will take the updated storage over time. Or if you're assimilating the storage, then we can provide a series of the observed storage values in the module detection function. And the output of this module detection function gives us a module number. And that module number corresponds to a different set of rules. So as Dr. Cai had shown in the previous slide, we had a tree algorithm, and then module one example had different sets of if-then conditions. So those become the release function. This provides us the release, and that can be either used to update the storage or not, depending on our preference. This is the same method we used in the Mississippi scale model that Dr. Cai was talking about. And if we had a vector-based model, we could always treat the reservoir as a node in a stream-link network. And that's the way we did it for the watershed scale model, in which the reservoir was a node. It received flows routed by the hydrological model from upstream, and then it was transformed as release that goes downstream. In the next two slides, I'm going to dig into what these module detection function and the release functions look like and how we can get them. So one of the trademark advantages of GDROM is that it's provided as text files, which are very interoperable. We don't need to depend on a certain coding platform to use it. Text files can be opened by anyone. And so we have these text files for the module conditions, and we have the modules themselves, which are the release functions. So for each reservoir, we have at least two text files, the module condition and the modules. And then depending on which reservoir it is, if we have various modules for that reservoir, then it can range from 1 to 8 different number of modules in the modules. So the module condition file takes the inflow, the PDSI, the DOI, etc., and the output it produces is the module number. And this module number corresponds to a set of rules, which is on the right-hand side over here. Of note, the same inflow and storage can produce a different release if it was a different module. So if in module 1 receives the same inflow and the same storage, it will produce a different release. So we need to be careful about which module we're working with. And the module file itself forms a release function, and the output of it is the release, depending on the inflow and the storage conditions. Now, of course, we don't need people to convert these text files into their own code platforms. And for that increased flexibility, we've also provided a script that can convert all of these text files into C, R, or Python function files right now. And this is aimed to cover a broad base of users who might be using different coding platforms. And the example over here is for a C function that's produced using those text files. Each of these functions is uniquely identified by the grand ID of that reservoir. So the grand database provides IDs for each and every reservoir, and that's how we identify each function differently. Within each function, we have the same conditions which we had in the text files before, but according to the syntax of the coding platform we have. And so that's how we can convert these text files into any function that we can call in our hydrological model, depending on when we need it, when the reservoir occurs in the streamflow network. Of course, we also realize that Python is a very popular coding platform. And so for increased ease of use, we've also developed a package called GDROM ops, which includes all of these GDROM functions already in the package. So the user doesn't need to go in, use our script to convert these text files into functions. They're already present here. And so we're going to show how this thing can be used to run a reservoir simulation in Python. And for this example, we are taking the node link framework. So the red colored reservoir is a node present in this stream, the upstream link and the downstream link. And the inflow for this is provided by the hydrological model. And then this node, which the reservoir operation rules are provided by GDROM, converts that into a release. So the framework goes as follows. We import GDROM ops, which is a package in Python, and it's a pip. We can pip install this package And then just like the previous slide, we have a grand ID that identifies each and every reservoir. So we provide the grand ID, and accordingly, the package will find the correct rules to use for the simulation. We develop those rules. We call those rules using rule engine, which is a function in the package. And then after this setup, all we have to do is provide the inputs, which are the date, the inflow, storage, DOI, and the inflow is produced by the hydrological model here. And then we can get the outputs as a simulated release if we are only simulating the release and assimilating the storage, or we can get the release and the storage depending on our preference. We also have an example of the code here. So we are doing pip install GDROM ops. This gets the GDROM itself. And then rule engine is the function within this package, which is used to generate the rules itself. We are identifying rules for grand ID 41, which is a reservoir. I think that's like a reservoir. And then we use the rule engine function to get all of these rules as the ENG object. So this engine object forms all the rules that are present here. DF is the input that we're providing. So it can either be a CSV that we have preloaded, or DF can be a data frame that is produced using the inflow for the hydrological model. So this blue box up here can be DF. It goes into this ENG. That's a method we have simulate release. We provide DF to it, and it gives us out, which is over here. Out is the release that is simulated. And so how do we actually get these rules if we wanted to go with the raw data? We have two sets of files which are uploaded on HydroShare and can be publicly accessed. We have the original GDROM, which consisted of 452 reservoirs. We also have an extended version with 2017 reservoirs. And along with the modules and the module conditions themselves, we also provide the raw data. So we have the daily time series of all these reservoirs of inflows, storages, releases, etc., and the metadata for each reservoir. And we are very happy to report that the original GDROM version has been viewed over 4,000 times and downloaded over 1,200 times. And people have used it, and we are very happy about that. So I'll move it over to Dr. Cai again for the extensions on V2.
I'm sorry, I don't have much time for the extension, but I just want to say now our current GDROM is developed with some data-rich reservoirs, but we have made some progress to show with limited data, we can generate reasonable model. Like if we could couple hybrid empirical and conceptual components together. So we have a paper under review. And our GDROM version 2, so we use data fusion approach to combine multiple data sources together. We use a transfer learning method to generate GDROM for data limited reservoirs. So the good thing is I heard my new project has been funded, and through this project, we're going to increase the accuracy of the model. As I mentioned in the presentation, our GDROM still miss some of the details are still not there yet. So very quickly about some remarks. I just want to say our GDROM for this 450 reservoirs, they are fully available for testing and application. So actually, it has been already used in SWOT model. And then for version 2, for 2017 reservoirs are available for testing, and they still under improvement for accuracy check. And so this second kind of global GDROM, we call this as a C plus GDROM. This is available for testing for any reservoirs around the world. As Anav just said, we're ready to share our products, especially for the 452 reservoirs. So we have data, model code, and manuals publicly shared. So for the users, you really just need a very minor work to incorporate our products into Reservoir, into your hydrological model. Thank you very much. I hope I have a few minutes for questions.
Thank you so much, Ximing. We would love to hear if we have some questions from the audience. Please feel free to raise your hand or unmute and ask your question yourself. Who would like to begin? James, let's hear from you.
James, hi.
Thanks, Jim.
James. Yeah.
Thanks. Can you hear me?
Yes, yes.
The generalizability, that's the question I'd like to ask about. So, I mean, the methodology has produced a set of modules that are generalizable, but the training is individual per reservoir. That's
Yes, perfect. That's right. That's right. Yeah.
Is there, do you have any interest or have you explored finding, like, you know, so the national water model, for instance, has lots and lots of reservoirs. Most of them are represented with very simple parameters. Is there something that we could do for some of the simpler reservoirs where we don't necessarily have an observation that we can calibrate a set of
Yes.
modules to?
Yes.
Good.
Yeah, sorry. I already understand your question, James. Yes. So actually, I did not have time to show the details of a C+ GDROM, and that one actually it could be used for any reservoirs, even without data. So we could use some default variables, default parameters. Only if we have like a few years data, it could be very helpful, and it takes advantage of remote sensing data. So you might notice that remote sensing data provides a lot of opportunities to estimate the reservoir surface area and also the storage. And we have worldwide data availability for that. Yeah. So we can talk more details, James. I can probably share with you the manuscript, which is under review.
Thanks.
Thank you.
Yeah, Don Call.
Hey, Ximing, thank you for the presentations. I have a few questions. In terms of compatibility, you mentioned that GDROM is kind of compatible with the hydrologic model, which is maybe CFE or land surface model, but GDROM also can be compatible with the maybe channel routing model or kind of vectorize the channel network so that reservoir can directly get inflow from the channel.
Yes. Oh, yes, that's true, right? That's true. Basically, wherever you need, you have a reservoir and you need to then you just call the reservoir by the ID to your model code, and then you will be able to get the reservoir code, the engine function, as Anav just explained, from our database, publicly available database.
Okay,
So
thanks. And then,
yeah.
Go ahead.
Basically, you treat the reservoirs as some nodes in your network, right? In your stream network or watershed network, and whenever you need it, you just call an external function. You call that will bring the reservoir modules and the GDROM code into your model and run internally using the hydrological model.
Okay, and my second question, the last question, is that maybe some kind of reservoir, like some kind of federal reservoirs, they kind of working in tandem, which means that upstream reservoir, it depends on the downstream reservoir, maybe storage conditions. This GDROM has some kind of capability to consider that kind of conditions as well?
That's a very good question. We were asked many times by people. So although many of these reservoirs, they are operated by a group, right? But we assume we could identify the behavior, the operation rules for any reservoirs based on their data, their own data, inflow, outflow, storage. And we believe this is kind of joint operation in some way captured by either the inflow or the reuse. Yeah, but this is certainly a question for additional research. We need to test that. Make further testing. But so far, as Anav just said, we test this with many reservoirs on the Mississippi River Basin, and some of these reservoirs they are operated by group jointly, but we still find out significant improvement in terms of the flow simulation. Right.
Okay, thanks.
Yeah, thank you.
Okay, everyone, we are right at the end of our time that we have together. I'll be happy to share the recording of this event along with Ximing's email with the participants here and then the entire consortium as well, so that you can follow up with any questions. And thank you again to Ximing, Anav, and Zihan. We really appreciate the time that you've dedicated to us, and we look forward to seeing you all in the consortium at the next R202R webinar. Thank you so much.
Thank you.
Thank you for your attendance.